Sir, shall we start? Hello, sir.
जोशी सर सुरू करायचं.
Sir,
हो,
sir.
no problem.
ओके. स्पीकर.
Okay. Good afternoon to all present here on virtual dais. Today's resource person, Dr. Sandeep Joshi, our principal, Dr. Sanjay Bokade, Vice Principal, Dr. Sanjay Deshmukh, Head of the Mechanical Department, Dr. Rajesh Kale, Technical, Teaching and Non-Teaching staff, and all participants. I, Narendra Mustekar, on behalf of MCT's Rajiv Gandhi Institute of Technology and Department of Mechanical Engineering, welcome you for all for first day, second session of AICTE AQIS sponsored online 1 week short-term training program on recent trends in energy management and audit. Today, we have resource person for this Sttp, Dr. Sandeep Joshi, with us. He will speak on energy forever, renewable energy in India, and energy management in solar agro product dryer. I take this opportunity to introduce our today's resource person, Dr. Sandeep Joshi. He has completed his diploma in mechanical engineering from Government Polytechnic, Dhule, BE in mechanical engineering from MGM's College of Engineering, Nanded, MTech mechanical with thermal fluids from Dr. Babasaheb Ambedkar Technological University, Lonere, Raigad, PhD mechanical from Indian Institute of Technology, Mumbai. He has also completed diploma in material management from Principal Dr. Ellen Velankar, Institute of Management and Research, Matunga, Mumbai. He is presently working as a principal, Pillai College of Engineering, New Panvel. He has patent on solar air heater, also 12 papers in international journals. His expertise is in utilization of solar thermal energy, thermal and fluid engineering, heat transfer, and waste heat recovery, solar energy, and energy management. I welcome you, sir, and thank you for joining us today. I request you to enlighten us with your knowledge on session topic. Thank you, sir.
Yes, thank you, Bostekar sir, for wonderful introduction and your kind words. Actually, it's an opportunity to interact with teaching fraternity through such faculty development programs or short-term training programs. It's my pride and privilege to discuss about the subject matter with all of you. Let me share my screen. Is it visible, sir? Is my screen visible to everyone?
Yes, sir. Yes, sir.
Yeah. So thank you once again, and my name is Sandeep Joshi. Namaste, everyone. I am working in Pillai College of Engineering, New Panvel, and let us discuss on this topic: energy forever, renewable energy in India, and energy management in solar agro-produced dryer. Why specifically I have chosen this topic about solar agro-produced dryer is, of course, it's my own interest. It was my research topic, and we have a couple of patents on solar dryers. So I felt that I must share my experience about solar agro-produced dryer and energy management in solar agro-produced dryer with all of you on this good and wonderful occasion. So these are the points which we are going to discuss today. One is conventional energy sources and their limitations, the need for non-conventional energy sources, then Indian energy scenario, conventional as well as non-conventional both, and then we'll discuss about few topics related to renewable energy in India. And very important is HRD strategies, human resource development strategies in Indian context, because this is the Sttp short term training program, and I understand that majority of the participants are from teaching fraternity and seniors, and we all are constantly in touch with the younger generation or the students or the budding engineers, and we must convey them that what are the human resource development strategies uh, referring to Indian government and in context of renewable energy sector in India, so that they can tune themselves to design their wonderful career in renewable energy sector. Uh, that's why I have included this topic, that HRD strategies. And then the second section of the presentation will be exclusively on solar agro-produced dryer, which we developed at IIT Bombay, and the energy management in the solar agro-produced dryer. Of course, first couple of slides are very common to all of us, but I have tried to put it in the other way to understand the limitations of conventional energy sources, and accordingly, once we are done with that, we will have a very wonderful ground or platform to develop the need for non-conventional energy sources, and then we will talk everything about non-conventional energy sources or renewable energy sources in Indian context. Let us begin. So energy is the key input to drive and improve the life cycle. It is very true that consumption of energy is directly proportional to the progress of the mankind. We can recall our earlier childhood days when at some places there were only kerosene lamps, or at some places there were those fluorescent lamps, and then gradually now we are living in very wonderful light environment in our day-to-day life, and it shows our progress also. So consumption of energy is directly proportional to the progress of mankind. The global demand for energy is continuously increasing significantly, and the reasons behind that are ever growing population, very important reason, improvement in living standard of humanity. Day by day we are trying hard to improve our living standard, and industrialization happening all over the globe. These are the three main reasons which are the main cause behind increasing the energy demand continuously. World's most of the energy needs are derived from conventional sources up till now. The fossil fuels such as coal, oil and natural gas are the major resources of the energy even for today's world. And these fuels are often termed non-renewable energy sources because they are going to run out in a short time. Although the available quantity of these fuels are extremely large, they are nevertheless finite, and so will in principle run out at some time in the future. There are some theoretical calculations for this. So how long will fossil fuel last? So if we consider the energy density of fuel is about 10,000 watt hour per liter, means out of 1 liter of fuel, if we are able to generate 10,000 watts per hour, that is the density of the available conventional fuel, and energy content in the fuel within the earth, if we consider entire earth, the total globe is full of fossil fuel, then it will be approximately 1.1 into 10 to the power 21 kilowatt hour. And considering the energy consumption, we can easily calculate that this fossil fuel will get depleted in about 368 years, considering the entire earth is full of fossil fuel, which is not. So obviously the timeline for depletion of fossil fuel is very short. Of course, referring to lifespan of a human being, that may be big, but at some point of time we are definitely run out with these fossil fuels. So the total world's energy requirement is fulfilled by various sources, and the contribution of these sources is as follows. Say we are generating about 40%, or we are uh, mm, satisfying our energy needs by oil about 40%, natural gas 22.5%, coal 23%, hydro is 7%, nuclear is 6.5%, and biomass and other sources is 0.7%. Purposely, I have included biomass also in this fossil things. The reason behind that you will come to know in next couple of slides. Having done with this, we can conclude few things, that world is gradually marching towards a severe energy crisis. We don't know what is going to happen with this ever increasing demand of energy, and if it oversteps its supply, which is already overstepping. In India, if we consider Indian scenario, then we have already overstepped the demand and supply ratio. The demand is always more and supply is less, and that's why majority of the time the rural India is facing the power cut. It is always known that energy we use every day is not limited, yet we take it for granted. We all are aware that energy which we are using is not unlimited, it is limited, but still we are taking it granted, and we are utilizing the energy without taking proper care. When I say we, I am not referring to the government, but to all of us, the common people. This is our general habit, that whatever is happening, we are simply blaming to our government. But what the government is, government means we all. We all are wise enough to understand this particular statement. So I will not go into much details of this particular statement, but we all need to understand that whatever the scenario, whatever the crisis, not the government, we all, common people, common Indian people, or entire mankind, human beings across the globe are responsible for that. World's total primary thermal energy demand is about 13 terawatt, and it is predicted that we need to the demand will be doubled or tripled in next 30 to 50 years, considering uh, the rise in the population, enhancement in the lifestyle, and the industrialization, the three basic reasons behind that. So considering this, we need to replace 13 terawatt of carbon emitting primary energy and need to generate 26, I am considering double only, 26 terawatt more new carbon free energy in the next 50 years. Two very important uh, uh, words here are carbon emitting primary energy and carbon free energy. Majority of the energy generated is carbon emitting energy right now, and we need to replace it with carbon free energy. If we consider this uh, rate of increment from 13 terawatt to 26 terawatt in next 50 years, we need to build 40,000 nuclear power plants, which are that way carbon free. So if we simply write down the time scale for that, 50 years is equivalent to 18,250 days. This is very simple and basic calculation. And in these 18,250 days, we need to build about 40,000 nuclear power plants. So we need to build 2 nuclear power plants per day worldwide in next 50 years. Is it the achievable target? Certainly not. So we need to think on this, and being the technocrats, we need to find out the solution for this. What will be the solution? Before that, we need to prepare the ground for this, the need. In last 7 decades, considering India, the India's energy use is increased by 16 times, and whereas the installed electricity capacity is increased by 84 times. Just understand these numbers. Energy use is increased by 16 times, installed electricity capacity is increased by 84 times. Even then, demand has consistently overstepped supply. Still, we are unable to match the demand and supply, referring to electricity requirements. The recent numbers I have given here, in 2019, India's electricity use was the 5th highest in the world, out of which about 35% of primary energy needs are ensured through import. We can imagine the amount of rupees we are consuming on this primary energy need. The country's overall power deficit was 12% in the financial year 18-19. This deficit is risen steadily from 8.4% when India was free to 11% in 2006, and since then the deficit is ranging between 11 to 12%. We never able to cross this deficit, to overcome this deficit. The government has plans to provide universal access and to increase per capita consumption of electricity, and it is currently 1181 kilowatt. Why it is necessary to think on this is, in the first couple of slides we have said that the progress of mankind is directly proportional to electricity consumption. So if the electricity consumption is more, the lifestyle is well established in the society. So that's why it is very important. Now, out of this total energy generation in India, about 79.8% is generated from fossil fuel and about 17.3% is from renewable energy. These numbers have to be exchanged, and that is what is the target of Government of India also. What is the reality? About 1 lakh villages till date are remain unelectrified, and almost 400 million Indians are without electricity coverage till date. This requires the resources of about 9 lakh crores, the huge amount, from where we are able to build this particular amount. It's difficult. So it is very important to switch from non-renewable to renewable. Being the energy consultant, I am thanking the ever-increasing demand and the increasing shortage of energy resources and the rapid increase in the prices of the fossil fuels in last few years, because that has opened the eyes of all the Indians, and everybody has started thinking to switch from conventional to non-conventional energy sources. But are we equipped to face this energy crisis, if at all it comes? What can you and I do to tackle it? The steps are very small, and with that we can address majority of the problem. To start with, we need to understand the importance of energy in our lives and stop taking it for granted. We have to minimize the use of oil, gas, electricity or any other fuel, because these are carbon emitting fuels. And if at all we wish to give better environment to our kids or our future generations, we need to start from today itself and from our house. We cannot afford to waste any available energy. Simple things like using a public transport as far as possible, switching off car engines at traffic lights, and minimizing the use of gas and oil in everyday activities will help a long way in crisis readiness. Another thing which we can do is rapid deployment of other technologies like hydro, wind, solar, and biomass, which are comparatively renewable. And instead of concentrated uses of energy to distributed uses of energy, we need to shift. Right now, we all are using the concentrated energy. Means we might be having a big hydropower plant, a big dam, generating the electricity there, and we are supplying it to all over the country. Instead of that, we need to think about distributed uses of energy. Means maybe if we use solar energy, our own terrace can be utilized to satisfy that particular house energy requirement. That is what is distributed uses of energy. What is the potential then? We are talking about renewable energy. What is the potential of India? Increased recognition of the contribution that renewable energy can make to energy independence, climate change mitigation, rural development, and improved health and lower health costs. This last point is directly linked to air pollution. If the air is polluted, many of us staying in Mumbai or other big cities of India might have realized that if there is no pollution, there are no health issues in last 7-8 months of pandemic. India has a vast supply of renewable energy resources. The potential of renewable energy in India is about 896, about 900 gigawatts. Till now, the total installed capacity based on these sources is about 87 gigawatt. It is just 7% of available resources. These are the numbers of 31st March 2019. Now this 87 gigawatt is distributed as follows, that from wind we are able to generate 37 gigawatt, from small hydro we are able to generate about 5 gigawatt, from biomass about 9 gigawatt, solar energy about 35 gigawatt, gasifiers 450 megawatt, and urban and industrial waste hardly 150 megawatt. The numbers are very meager, and we all need to think on this, and we have to increase these numbers. India is the only country in the world having exclusive ministry for renewable energy development. That is the Ministry of New and Renewable Energy, MNRE. So government has taken its steps. We need to support the government by switching from conventional to non-conventional using the technologies available. Renewable energy is the energy from a source that is replaced rapidly by natural process and is not subject to depletion in a human time scale. Of course, nothing in this world is renewable or replaceable, referring to human time scale. If we consider the human time scale, then majority of the sources are renewable sources. India ranked third most attractive country to invest in renewable energy. USA and Germany are first two. Now, when we talk about renewable energy in India, what all are the sources we need to consider? First is wind energy, then small hydropower. I am not saying hydropower, I am specifically talking about small hydropower. The smaller hydropower plants, not the bigger dams, because bigger dams are having their own inherent difficulties and problems. Then solar energy and biogas energy and cogeneration. Cogeneration is referring to industrialization. We are talking about growth in the industrialization, and in every industry there is a waste heat. So it can be utilized for power generation, and that is what is the cogeneration is. Similarly, biomass gasification and energy from urban and industrial waste, and ocean energy. Ocean energy specifically I am talking because we have huge this ocean banks. Let us discuss little bit in detail about wind energy. Wind energy is making a significant contribution to grid power installed capacity of India. It is emerging as a competitive option. So India's wind power potential is about 302 gigawatt at 100 meters height. Means the hub of the turbine has to be set 100 meters above the ground level, and that is 302. If we consider about 50 meters, then this number is uh, about 50%. Say maybe about 200 gigawatt is possible to generate at 50-meter height. For sites having wind power density greater than 200 watt per meter square at 50-meter hub height, and assuming the land availability in potential area about 1% and requirement of wind farms about 12 hectares per megawatt. This estimation 302 gigawatt is based on this: the availability of land about 1% of potential area and the requirement of wind farms. To have a wind farm to generate 1 megawatt of wind power, we need to have 12 hectares of land. So these are the major constraints referring to wind power potential in India. Referring to states, Tamil Nadu is maintaining its lead in wind installation since last so many years. About 50% of total capacity of India is generated in Tamil Nadu. Wind turbines of 1, 1.25, 1.5 and 1.65 megawatt are being installed across India in large numbers, and government is giving subsidy in development of wind farms. Asia's largest wind turbine generator of 2 megawatt capacity is installed at Chettikulam in Tirunelveli district of Tamil Nadu. So these are some facts and figures referring to wind energy in India. Important thing is Tamil Nadu is at the top referring to generation of wind energy. Coming to small wind energy plants and hybrid systems, small wind energy system harness wind power potential to meet mechanical and electrical power requirements in decentralized mode. Okay, maybe a small wind farm, and it will suffice the requirement of that particular place. Say for example, water pumping, aerogenerators and wind solar hybrid systems may be installed on the terraces of the societies in the big cities. Such systems are useful for deployment in several rural and remote areas of India, which are unelectrified or have intermittent electricity supply. If a farmer can develop a wind farm or a wind turbine in his farm, he may not have to rely on the electricity supply of MSEB, which is very intermittent. The ministry is implementing a program on small wind energy and hybrid systems with main objective of field testing, demonstrating and strengthening the manufacturing base of water pumping windmills, aerogenerators and hybrid systems, and undertaking research and development for improvement of designs and efficiencies of the system. Lot of funding is available even for teachers from MNRE. We simply need to visit the MNRE website and understand the specific requirements to submit a research proposal. An aggregate capacity of 484 kilowatt of such systems installed under the scheme, and the unit capacity ranges from 1 to 10 kilowatt. So you can develop a wind power plant of 1 kilowatt, which may suffice the needs of your own house, and even for that you will get some funding from the government. Such systems are mostly installed in Maharashtra, Goa, Karnataka and West Bengal, but the installations are not sufficient. We all really need to think on this, and we need to convey this to our students also. This is the form of decentralized power generation, the small hydropower plant. Okay, we are not talking about big dams. These are very small hydropower plants. All projects between 3 megawatt and 25 megawatt are considered as small hydro projects. Small hydropower SHP. Such projects essentially harness energy from flowing or falling water from rivers, rivulets, artificially created storage dams or canal drops. At many places in the rivers, we are seeing the turbulent flow of the water. Local bodies need to think on this, and such places can be converted as energy reservoirs to suffice the needs of small villages or small towns even. These projects are increasingly becoming economically viable. They can play a role in improving the energy position in some parts of India, particularly in remote and inaccessible areas where there are rivers or maybe artificially created storage dams, small storage dams can be created, and the available hydraulic energy can be converted into hydropower. Gestation period and capital investments are getting reduced in solar hydropower projects. Small water streams are being tapped in hilly areas, and canal drops are being exploited for generation of power in the plain areas. Multiple opportunities are available. Only thing is we need to open our eyes and we need to tap the opportunities available. How much is the estimated potential of small hydro projects in India? Government has done the survey of various places and various locations in India, and the estimated power generation capacity is about 150 gigawatt electricity, all of which might not be technically feasible and economically viable, but can be given a thought. Technically feasible potential of identified sites are about 4,400 in number, or which can generate about 10 gigawatt of electricity. The, the sites which are already identified by Government of India and which are technically feasible to set up a small hydropower project there is about, it will give us about 10 gigawatt of electrical energy. And if we think in a decentralized manner, it will help us in addressing the problems of small towns and small villages. We can make them independent. Just recall that movie Swadesh. The same concept was explained in a dramatic way in that particular movie. These are the potentials of identified small hydropower sites up to 25 megawatt capacity. So state-wise numbers are given. In Maharashtra, about 234 such sites are identified, and which may have a total capacity of about 600 megawatt electricity generation, out of which 25 sites are already in place and which are generating 208, about 209 megawatt of electricity. And project ongoing projects are at 4 different sites, and which will add 24 more megawatts in the existing capacity. The highest capacity of small hydropower generation is in the state of Uttaranchal. There are 354 sites identified, and which will generate about 1.5 gigawatt of power using small hydropower plants. Moving ahead, solar energy. This is just, I am calling the solar energy as father of all the energy sources, because if there is no sun, you will not get wind. If there is no wind, wind power is nowhere. If we don't have sun, we will not get rain. If rain is not there, no hydropower. So solar energy is very important, very important. Only the drawback of solar energy, it is decentralized. We need to concentrate it, and the concentration technologies are now well established and developed, which will, using those technologies, will make the solar power plants very much feasible. Exploitation of solar energy has been one of the major programs of MNRE, or maybe we can say Government of India. Solar energy, which is manifested in the form of heat and light, is harnessed through solar thermal energy or solar photovoltaic energy, and now the upcoming area is combination of solar thermal and solar photovoltaic. I have already started working on combining solar power, solar thermal and solar photovoltaic, and maybe in next 6 months or so we might be coming up with some technology which will combine this, which will give you hot water as well as required electricity in within your area. Means whatever the area available for you, you need not to divide it for power generation and for solar water heating. With the same area, you will get hot water as well as solar power. And these solar thermal and solar photovoltaic are having applications like cooking, water heating, drying farm produce, water pumping, home and street lighting, power generation for meeting decentralized requirements in villages, schools, hospitals, etc. In spite of the limitations of being a dilute source and intermittent in nature, solar energy has the potential for meeting and supplementing various energy requirements. In earlier days, the initial investment was the major hurdle in uh, in in reaching out with the solar energy resources, because the initial investment is too high. In those days, government used to give subsidies on installations of the solar water heaters or solar photovoltaic plants. But thanks to the uh, developed technology, now the initial investment cost has reduced down in multiple folds. India, being a tropical country blessed with plenty of sunshine, average daily solar radiation varies between 4 to 7 kilowatt hour per meter square for different parts of India. For average calculation, the solar intensity in India, the radiation intensity in India is considered as 5.5 kilowatt hour per meter square on an average 250 to 300 clear sunny days in a year, and the sunshine time on an average for every day is about 7.7 and a half hours. It's a significant time, and we can generate ample amount of energy. We can convert the solar energy into ample solar thermal energy, as well as enough solar photovoltaics also. India receives about 500 trillion kilowatt hour of solar energy in a year. Only thing is, it is decentralized. Otherwise, only solar energy can suffice all our requirements. The beauty of this, it is environment friendly and freely available locally also. No one can stop you in utilizing the solar energy. Though energy density is low and availability is not continuous, it has now become possible to harness this abundantly available energy reliably by converting it to suitable or usable heat, and through direct generation of electricity. The solar thermal energy utilization, as well as solar photovoltaic energy utilization. Both the things are possible due to the developments in the technology. Conversion systems are modular in nature. The advantages of solar system are, the conversion systems are modular in nature. Means the solar collectors, which you can get from maybe half a meter square to multiple square meters, and you can use those modules as per your requirements and as per the availability of the area, can be appropriately used for decentralized applications. No need to have thousands of square miles required to establish the solar power plant. You can have your own solar power plant on your rooftop itself. Several technologies have already been commercialized. Some are still under development. Of course, when it comes to technology, though it is commercially available, but it is continuously developing. So we can make a statement that every technology is always under development state. Main objectives of the solar thermal program of Ministry of New and Renewable Energy Sources of Indian government is to develop and promote the use of these technologies in order to meet the heat energy requirements in domestic, institutional and industrial sectors in India. When we think about educational institutes, the subsidies are available to set up their own solar power plants on the rooftops of institute buildings, even for industries and even for domestic utility. To generate electricity in an environment friendly manner, these are the main objectives of MNRE behind this solar thermal program. For harnessing the enormous potential of solar energy, MNRE is implementing a variety of programs like solar photovoltaic program, solar grid power program, and solar water program. If you visit MNRE website, you can open up the doors for you, for yourself, to to write the research proposals and to work to continue researching in this particular area. Lot of funds are available. Coming to solar photovoltaic program, India ranks 5th in the world among the PV module manufacturing countries. Right? Photovoltaic modules is the basic requirement to have the solar PV plant. Cost of PV modules is gradually decreasing. Today, the PV technology has become cost competitive to other technologies based on conventional energy for meeting power requirements of small load in remote areas. When I started working with solar energy utilization, the cost of solar PV was about 250 to 300 rupees per watt, and now that cost has come down to 50 to 65 rupees per watt. There is a drastic reduction in the cost of PV modules because of enhancement in the technology, and that has reduced the cost of solar PV plants. There is a need to bring down the cost of PV modules further so that PV technology becomes commercially viable. Now it has become little bit commercially viable, but it is expected that in next couple of years this cost will come down to 25 to 30 rupees per watt and the PV module, and automatically the cost will reduce, the total cost of the power plant will reduce and the technology will become viable. Under the solar photovoltaic program, demonstration and utilization program, grants in aid is given to the implementing organization for providing subsidy to the users for purchase or installation of solar home systems, solar street lighting systems, standalone power plants, building integrated photovoltaics, etc. And you might have noticed in previous 6-7 years at many places like municipal gardens, even street lights are solar street lights, or solar lighting is made available in the gardens also, and that is what is the outcome of this grant in aid given by the ministry and the subsidies provided by the ministry for installation of such plants. Total of 60,000 solar photovoltaic home lighting systems, about 6,000 street lights and 27,500 solar lanterns were allocated to various states and union territories. This number is just 2 or 3 years back numbers. This number might have increased right now. About 3.24 lakhs of solar photovoltaic home lighting systems, 0.53 lakhs solar photovoltaic street lighting systems, and standalone ST power plants of an aggregate capacity of about 1.8 megawatt power have been installed since inception of this program. The government is giving lot of support. We need to come forward and make use of the available grants. The solar grid power program has two components. One is thermal conversion technology and the photovoltaic technology. Before this, we have discussed on two separate technologies. One is solar thermal, second one is solar photovoltaic, and now we are discussing about solar grid power. It has two components. One is thermal conversion technology and another one is solar photovoltaic technology. The solar photovoltaic technology converts sunlight into electricity without any pollution, whereas solar thermal conversion, maybe we need to harness the solar energy, we need to generate the steam using the solar energy, and we can run the steam power plant. Okay, a very raw and very basic example. 34 grid interactive solar photovoltaic power projects have been installed in India with the installed capacity of 2.8 megawatt, and 6 more projects with an aggregate capacity of about 400 kilowatt are under installation in India itself. Solar grid power technologies are not yet commercially viable. At present, the juncture they serve the purpose of technology demonstration is all these power plants, 34 plus 6 upcoming, are technology demonstration projects, and sufficient experience in installation, operation, maintenance, and other aspects of grid interactive power plant has been gained out from these projects while installing these projects. Referring to present technological advances, these technologies will start becoming viable from this year onward. Means the purpose is served. Whatever the SPV power projects are established, they have served the purpose. They have given enough experience to all our engineers about operation, maintenance, and other aspects of grid interactive power plant. And using this experience, we can further grow and we can further utilize this, further develop this solar photovoltaic power projects in India, so that we will have pollution-free environment. Coming to solar water heating now, this is very domestic purpose. One of the areas of solar thermal technology in heating of water for domestic, commercial, and industrial uses. Many of the hotels and the tourist places have started installing solar water heaters on their rooftops, and uh, the payback period for such systems has also come down as less than 1 year. So the initial investment is recouped within a year, and after that, with a small maintenance, they can simply save their uh, money. India has been making and using solar water heaters for almost 3 decades. We can say 4 decades also now. These systems are becoming increasingly popular for hotels, hostels, hospitals, and other large institutions and industries. These systems with total collector area of 10 lakh meters square have been so far installed. State governments have been advised to make necessary provisions in buildings to incorporate solar water heating systems. Few cities in India are not giving permissions for new buildings unless and until they have the provision for solar water heating system. If you remember, or you might have heard that Thane city is declared as solar city of India. Majority of the street lights in Thane city are uh, are using the solar energy harness. When solar water heaters replaces an electric geyser, it is not only saves electricity but also reduces the peak load demand. In the morning, electric geysers are mostly used, and at many of the places you might have faced the power cuts in the morning sessions. So if you install the solar water heaters in the morning, there will be no load on geysers, and automatically the peak load demand will come down, and it will help the rural areas where there is always a power cut. Domestic solar water heaters of 100 liters per day capacity prevent emissions of 1.5 tons of carbon emission every year. So it is going to be a significant contribution referring to carbon emission. We all well aware about carbon credits also. So you can think over it and you can start switching from electric geysers to solar water heaters at your domestic places. This is very important for all of us now. Having done with the discussions regarding renewable energy sources, let us spend some time on human resource development strategies for Indian renewable energy sector. India has an installed capacity of 260 gigawatt, excluding large hydro, as on 31st March 2016, 4 years back. Renewable energy installed capacity is about 43 gigawatt almost, which is about 16.5% of the total power generation capacity. Currently, the wind sector contributes a major portion of this capacity. After that, the solar power, and after that, the hydropower. I have given latest numbers in one of the slides. You can refer that slide. And MNRE has ambitious plan for growth in all renewable energy sectors, some of which are generate about 20,000 megawatt from on-grid solar power by 2022 under the Jawaharlal Nehru National Solar Mission, and increase small hydropower addition from the present level of 300 megawatt per year to 500 megawatt per year in the next 3 years. So obviously, huge manpower requirement is going to come in these two sectors, solar and small hydro. And that growth, first we will discuss about global and then we will come to Indian requirement. So global employment in renewable energy is expected to increase 9 folds to reach a figure of 20 million jobs by 2030, with biomass leading the growth at 59% of total capacity, followed by solar PV and wind at 31%, which is more manpower intensive than the other sectors. Okay, say for example, if you install a wind power plant, the manpower requirement is very less there. But when you install the biomass, the manpower requirement is more. If you have a solar PV, the manpower requirement is more as compared to wind power. So that's why these sectors are called as manpower intensive sectors than other sectors. In the case of India, the employment opportunities would increase many folds by the year 2015 and 2020. There are a lot of solar based manufacturing companies have already installed and they have recruited many non-technical as well as technical people. If we consider first scenario, that moderate growth, even then the estimated employment by 2020 is 10,51,000. If we consider the high growth, then estimated manpower employment is 13,95,000. These are the estimated numbers. Maybe by this financial year end, March 21, we'll be able to get the new numbers, that how much we have reached to this 10,051 or whatever 13,095. The employment is balanced and well distributed across all the major renewable energy sectors. And the functional areas of employment include design, installation, fabrication, operations and maintenance, and project development and marketing. Means all the major sectors of renewable energy have the employment areas in these sectors. They need design engineers, they need installation engineers, they need fabrication staff, they need engineers and technocrats for operations and maintenance of the plant, and they need engineers and learned people or trained people for project development and marketing of the solar energy. We'll go into more details. If we consider wind, estimated current employment is 42,000 and by 2020 it will become 46,000. If we consider high growth, then it is 1,60,000. So huge ample opportunities are going to come in this renewable energy sector. Say for example, some 2 years back, this was the data of 2015, 2014, March 2014. So that time the estimated current employment was 3,50,000 and by 15 it was expected to grow by double. In 2020 it is going to be 4 times of 2014. Okay, so by 2020 the total employment will be about, the jobs available in renewable energy sector are about 14 lakhs. Only thing is we don't have trained manpower for this, and we are the people who can work for this. We can train our students, we can convey this to our students, and we can groom them with proper skills required for these sectors. What are the skills required? Planning and coordination skills in project management, erection, commissioning and grid integration of large scale projects, techno-commercial marketing skills, installation and commissioning skills, and after sales service and customer care. These are the skill sets which our students or the trained manpower has to have to make their career in renewable energy sector. The detailed report about job opportunities is available on MNRE website. I have given the website details also. Interested members can visit this website and they can find out the latest reports also, and they can understand the need of the program, and accordingly we can implement it in our day-to-day life as a teachers, and we can convey this to our students so that they can groom themselves or they can develop their skill sets required. So having done with this, let us enter into the second section of today's presentation, that is solar air heater for agro-produce drying. It's a simple, affordable, lightweight, one-screw collector for grid-independent operation for agro-produce drying. And we will discuss about energy management in this developed solar dryer. What was the background for taking up this particular program? That the applications and the technology gaps in flat plate solar collector technology for air heating. So considering the applications are very vast, right from drying the clothes to drying the agro produce to giving the proper temperature environment in the process industry for pasteurizing, for uh, uh, this denting and painting. Everywhere the high temperature air is required. Those are the applications. And even after having ample solar energy available, why the hot air collectors are not being utilized? The technical gaps are the required initial investment and the uh, very flexible air properties, thermophysical properties of the air. These are the two main defeating areas to serve the purpose of maximum utilization of solar heat in heating up the air and serving the purpose. So for that, we have developed a solar aluminum tubular air heater, which is simple and a modular design, can be built and deployed in rural settings. You can have a solar collector or solar air heater of 1 meter square area or half-meter square area as per your requirement of hot air, and you can have uh, hundreds of square meters of solar collectors with the same technology or with the same process. It's a lightweight unit. Use of glass is avoided, and glass is replaced by plastic glazing and lightweight aluminum absorber. It heats the air in one screw mode, that ambient air heated from 30 degrees Celsius to more than 100 degrees Celsius. In couple of experiments, we have recorded the hot air temperature coming out from half a meter of absorber tube is 119 degrees Celsius. The huge increment in the air temperature in the collector panel. It has a grid independent operation because the low pressure drop in the collector enables PV powered air circulation. So no additional electricity is required. Simple installation of one small PV unit will power the fan and it will circulate the air. It has very high efficiency by reducing the losses with multi-wall top cover, and it is very affordable. It gives early payback within a year. Whatever the initial investment is recovered in less than 1 year. It's a moderate temperature dryer, which is two types of dryers we have developed. One is recirculating dryer and another one is vertex type dryer. Why moderate temperature is required? Because majority of the agro produce have to be dried in less than 50 degrees Celsius hot air. Otherwise, only top surface of the produce will be dried, and the air and the moisture will be trapped within the product and it will start perishing. The dryer is tested for onion drying and chiku drying, and it is commercially available in the market now. What are the applications? The applications are industrial applications, commercial applications, residential applications, which consist of uh, heating at or below 100 degrees Celsius. The typical applications are drying, space heating, washing, pasteurizing, bleaching, dyeing and pickling. The collector was kept in the exhibition at Pune, and couple of laundry owners have requested us to install the dryers in their uh, cloth drying area, and since last 5 years they are very happy and very successfully uh, drying the cloth even in the monsoon season. The need again is fossil fuels are traditionally used for these applications. Reduced use of fossil fuel is desirable because of their increasing cost, concerns of pollution associated with combustion exhaust emissions is enabling us to move towards solar dryers. Solar air heaters can be good, clean and green alternative for the available electrical solar air heaters, electrical air heaters. And the widespread use of solar air heaters can be enabled by increasing heat delivered per unit investment, means amount of heat the solar collector is giving with reference to the initial investment. So if we are able to reduce the cost of the dryer, cost of the collector, and if we are able to increase the efficiency of the collector, obviously the heat delivered per unit investment is high. Okay, so monetary also we need to make the dryer very stable, and thermally also we need to make it very stable. Enabling grid independent reliable operation by reducing parasitic power requirements, and then enabling air circulation using photovoltaic will enable the widespread use of solar air heaters, and developing simple and maintenance friendly system. So the dryer which we have developed does not require any kind of maintenance. Instead, simple maintenance required is once in a week its top surface need to be cleaned. That's all. What are the technological gaps identified? The major constraint was single top glass cover is unable to reduce the top loss. The people from heat transfer area will better understand this, that the glass, if there is only one glass and if there is a radiation and re-radiation loss, the single glass cover will not help to reduce the loss. And if we want to put one more glass cover, it will add up the cost and it will add up the weight. Okay, so because of single glass and not controlling the top loss, it will reduce the efficiency of the dryer. And multiple, if we go for multiple top covers, it will increase the weight and cost of the dryer. Another thing is pressure drop. The typical heat transfer enhancement techniques increase the cost and pressure drop. What are the typical heat transfer enhancement techniques? Either we can go for highly conductive material, or we need to reduce the area. If we reduce the if we go for highly conductive material, it will increase the cost. If you go for smaller airflow areas, then it will increase the pressure drop. So use of high air velocity and multiple absorber configurations will increase the pressure drop as well as cost. And turbulence generation using corrugations, flow splitting and perforation will also increase the pressure drop. So single panel of 2 to 5 meters square is unable to deliver hot air at 75 to 100 degrees Celsius. By integrating several panels in series, resulting in large air side pressure drops and increased blower power, making PV powered blower with grid independent operations costly. So it is a need to develop a flat plate solar air heater which is simple to integrate and deploy, affordable, lightweight, capable of once through air heating up to 100 degrees Celsius, and be capable of grid independent operation. These were the objectives set, and referring to these objectives, a novel solar air heater is designed. What was the design philosophy? The design philosophy is the design has to address many of the technical gaps of commercially available solar air heaters, and it should open up the possibilities for use in various applications. Now, what the identified technical gaps, if we consider, the major gap was reduction in the top loss. So how can we reduce the top loss? We need to have multiple cover, At the same time, cost should not increase. At the same time, weight should not increase. So the glass covers are replaced by multi-wall plastic top covers. We have used twin wall 10 millimeter thick clear polycarbonate sheet. Now what exactly is this? If you have seen the skywalks in Mumbai city, the shades of the skywalks are of polycarbonate sheets. The similar kinds of sheets are used as top cover in the dryer. It has multi layers, so obviously it reduces the top loss. And the solar transmittance of that polycarbonate sheet is about 0.85. Of course, as compared to glass, it is less because glass has solar transmittance of about 0.95. And the conductance of glass is also little bit high. But when it comes to weight and cost, this multi-wall plastic top covers are very lightweight and the cost is also very less. So if you think 1 meter square of glass of about 4 millimeter thickness, it will weigh you about 10 kg, whereas this plastic cover is weighing 1.7 kg per meter square. So drastic reduction in the weight of the dryer. How can we reduce the back loss? It can be reduced by using rigid multi-layer insulation panel. The PIR 40 millimeter thick rigid foam insulation is used as the back cover of the air heater. It has very less thermal conductivity, hardly 0.01 watt per meter Kelvin, and very less conductance, and weight is also very less. So instead of having metallic cover at the bottom, which adds up the cost and which adds up the insulation cost also, the single sheet which has aluminum foil at the surface and foam insulation in between has served the purpose, and it has given the shape to the solar dryer. The side losses from the collector are reduced by integrating air inlet manifold with longer side of the frame. The solar radiation intercepted by the side frame is utilized for preheating the incoming air. Whatever the, I'll show you the drawing and you will understand it in a better fashion. The inlets are kept along the longer sides of the solar dryers, which are blackened, and they are also absorbing the solar heat, and they are giving the heat, absorbed heat, to the incoming air. So by that we were able to maintain the frame temperature near to atmospheric temperature, and obviously if the delta T is less between surrounding and the surface, the energy loss will be very less, energy convected will be very less. This is the diagram, you can see this is the polycarbonate sheet, and from here there are the air inlets, from here there are the air inlets. These are the tubes through which that atmospheric air is passed through, and centrally it is collected over here as a hot air. So there are two air inlets from both the sides of the collector. Air is sucked in and it is delivered, hot air is delivered centrally. So heat loss from the blackened absorber tube is reduced by minimizing the absorber surface temperature, which reduces the re-radiation and convection heat loss. Absorber surface temperature is reduced by improving heat transfer to air. This is the heat transfer fundamental. If we are able to transfer the available heat in a fast manner, we will be able to maintain the surface temperature near to atmosphere, and which will reduce the heat loss there also. Small diameter inner grooved aluminum absorber tubes, they have helped us in reducing the hydraulic diameter of the air passages, which has offered the inside heat transfer coefficient more than 15 watt per meter square Kelvin in laminar flow regime. Why it has been kept in the laminar flow regime is just to decouple the heat transfer coefficient and the pressure drop, because in laminar zone the Nusselt number becomes constant, and which gives, of course, the limited heat transfer coefficient, but with the less power consumption, and increase inside surface area available for heat transfer by having internal corrugations. Maintaining laminar flow of air inside the absorber tube helps decoupling pressure drop and heat transfer rate. Reasonable heat transfer coefficients are achieved at low velocities, which leads to low pressure drop and low circulation power. It has reduced the fan power and fan cost requirements by maintaining the laminar flow. And air temperature rise is increased by low air velocities and reducing the air mass flow rate per unit solar collector aperture area. So the amount of air which is passed through the collector was, the mass of that air is comparatively less, so that it will be heated up more. And the higher efficiency and lower airflow rate helps increasing hot air delivery temperature. And this has enabled us to heat up the air from 30 degrees Celsius to about 100 degrees Celsius in just half a meter length. If you see, the collector width is about 104 meters, and from both sides air is entering and delivered at the center. So this distance traveled by the air is hardly 500 millimeters, is 0.5 meters, and within 0.5 meters air is heated from 30 degrees Celsius to about 100 degrees Celsius by wisely and by wisely using the heat transfer concepts. This is what is the energy balance. This might be useful for all of us. Total insolation is considered as 1000 watt per meter square. Top loss is from this. See, this is what is the structure. This is the insulation panel. This is the flow area. This is the gap between cover and the flow area, and this is the top cover. I mentioned that multi-wall polycarbonate top cover is this one. So certain amount of insulation will be already lost because of reflection parameters of the particular material, and every material has some reflectivity index. So about, from this 1000 watt, referring to the properties of this material, about 56 watt per meter square will be reflected back, cannot be utilized at all. And by maintaining the temperature of this multi-wall cover near to atmospheric temperature, the radiation loss and convective loss are also kept within the limit. Hardly 12% is lost here. So 12 plus this 5, 17% of energy means out of 170 watt per meter square is top loss, 178 to be precise. Okay, now air has entered here. So this material, this might be having its own absorptivity coefficient, and accordingly about 22 watt is absorbed in this material itself, which cannot be used again. So 2.2% is lost here, right? Then again, this surface, because of its high temperature, it will radiate the energy. About 53 watt per meter square will be a radiation loss, which cannot be recovered. And because of the temperature difference, there is about 23 watt per meter square is the convective loss from this surface, which cannot be recovered. Of course, it is trapped within, and it is little bit utilized for preheating the air which is coming in the solar dryer. Now, about 850 watt out of this 1000 watt is transferred to the air. Okay, and by maintaining the laminar flow and by achieving the higher heat transfer coefficient, out of this 850 watt, about 807 watt per meter square is transferred to the air. So air temperature is increased from 30 degrees Celsius to about 100 degrees Celsius, and everything is trapped over here. And because of this PIR insulation, which is having very low thermal conductivity, hardly 25.5 watt per meter square is lost from the bottom. The bottom temperature is almost equal to atmospheric temperature. So very negligible loss is there. So if I put it in the balance sheet, out of this 1000 watt per meter square insulation, 178 watts are lost from the top, and 40 watts is from bottom and side loss. Heat delivered is about 782 watt per meter square to the air, and air temperature is air is heated from 34 degrees Celsius to 86 degrees Celsius in the calculation, with the mass flow rate of 15 gram per second. So if you convert it into grams per hour, you can simply multiply this 15 by 3600 and you will get it in kilograms, and it will be a significant number then. Okay. So this is the energy balance called as Sankey diagram for the solar air heater. So how the energy is managed in the solar agro-produced dryer is clearly disclosed here in this particular diagram. Now when the test is conducted, the size of the collector was this, about 2 meters square. One collector was installed with 24-volt DC fan of this model number and all other things, and the collector weight was 21.1 kg, so approximately 11 kg per meter square. The existing solar dryers, commercially available solar dryers, are weighing more than 35 kg per meter square, so very bulky. So this is very lightweight dryer, can be installed on any small vehicle and can be taken, and you can have a mobile dryer there. I am explaining the results of one of the tests here. The collector was installed at 43 degree inclination on the terrace of the lab, and why 43 degrees is depending on this the month. In the month of December, see, always we need to keep the solar rays perpendicular to the absorber surface. So to observe that condition, in the month of December, collector needs to be inclined at 43 degrees Celsius, and this is a mobile collector. Month wise you can change the inclination and you can maintain uh, the uh, the solar rays normal to the solar absorber. The average performance for 9 hours operation was, air inlet was 31.7 degrees Celsius and average outlet was 61 degrees Celsius. Referring to solar insolation, it is about 600 watt per meter square. You can compare this with the climate in the month of December in the state of Maharashtra. It's a winter season. Solar insolation is the intensity of insolation is little bit less. So available energy was 424 watt per meter square. Means out of 600, 424 watts are converted into hot air, and the airflow rate was 12.9, about 13 grams per second per meter square, and the efficiency achieved was about 70%, and the pressure drop is less than 50 pascal. If it is less than 50 pascal, even a small our computer fan can suffice the purpose of circulating the air in the dryer. Similarly, the peak readings are also given. At the peak, when the highest solar insolation recorded on that particular day was 910 watt per meter square, and the hot air was at the ambient air was at 35.6 degrees Celsius, and it was heated up to 81 degrees Celsius. So about 50 degrees of temperature rise with increased mass flow rate. Now if you see these two mass flow rates, the mass flow rate is driven by the solar powered fan. So it modulates the temperature of the hot air, is kept in the range of requirement of the hot air for drying, because the fan is modulating the air flow rate referring to the solar insolation available. So if the insolation is high, flow rate is high. So obviously you will be able to maintain the temperature. So if you see the temperature drop delta T is almost similar in both the cases. Of course, this is average because first couple of hours are having very low solar intensity and last couple of hours are also having very low solar intensity. I have already mentioned that average solar day in India is about 7.5 hours. Means the useful solar insolation is available for 7.5 hours in Indian day. Air side heat transfer coefficient achieved was about 18.3. So this heat transfer coefficient has helped us to maintain the temperature difference very low. Means the absorber surface temperature is hardly 9 degrees higher than the air temperature. So this has reduced the heat loss in the absorber surface. Sorry, large temperature difference on air side help reduce air velocities, typically 20 to 48 degrees Celsius, which resulted into laminar flow regime, which has helped us in decoupling the pressure drop and heat transfer coefficient. Pressure drop across the collector is 16 to 50 pascal throughout the day. The lowest pressure drop was 16 degrees and the highest was 50 pascal. And power required for suction fan is hardly 15 to 20 watts per meter square, which is less than 1% of the heat delivered by the collector. The total heat delivered by the collector was 424 watts per meter square, whereas the heat utilized for powering the fan was hardly 15 to 20 watts per meter square. It is hardly 1%, even less than 1%. We were here at the solar air heater. Now that hot air needs to be transferred to the drying chamber. So for that we need the air handling unit, and we need to have a very effective and efficient drying chamber. When the air is passed, it should carry the moisture from the produce and it should dry the produce. Why to dry the agro produce? To increase its shelf life and to reduce the transportation cost. So if you remove the moisture from the product, it will shrink. If it shrinks, then the transportation area requirement is less, because the weight is also reduced. In one go you can transport more mass of the agro produce and the cost will be reduced. Let us discuss few things about solar dryers. The solar dryers are of three types, basically of two types: active dryers and passive dryers. Active dryers are the dryers which are having fans to circulate the air, and passive dryers are the natural flow dryers. In both these types, again there are three subtypes. Integral dryer means direct type. The agro produce is directly exposed to sun rays under the dryer. Okay, direct drying. Distributed or indirect type means there will be a separate air heater, the type which we have developed and which is discussed here, a separate air heater and a separate drying unit. And a mixed mode means you can have a solar collector, at the same time dryer itself can be developed with the transparent material, so that solar rays can directly come in contact with the agro produce and you can have mixed effect on that. Having done with this, let us go back to the developed dryer. This was the air heater. This was the air heater, and below the air heater, this was the dryer. Okay, and the agro produce is kept in this particular dryer. The capacity of this dryer is 10 kilogram wet produce. Okay, we will discuss in detail about these things also. Now, if you see here, there are 5 dryers, 5 solar air heaters separately installed, and all these 5 are powered by this one solar solar PV module. Okay, the power requirement is very less. This is the test examples of onion drying. The procured onion from the market are 12 kg. Peeling loss, the onion need to be peeled and need to be sliced. So about 1 kg is a peeling loss. Onions are sliced and loaded in the dryer are about 9 kg. Moisture removed at day 1 is about 4.82 kg. Means this 8.9 kg was again weighed at the end of the day, and it was found that it remained 5.16 only. So 4.8 kg of moisture is removed in one day, with about 58% of moisture is removed on day 1, and on other day 45.7% moisture was removed. Okay, so this 8.9 kg wet onion was converted into 1.71 kg of dried onion. The total moisture removed in 16 hours is 6.87 kg, that is 77%, with a drying efficiency of 40%. The collector efficiency was 70, but the drying efficiency was 31%. Okay. So around 2.1 kg onion slices were kept under open sun drying also, just to compare what is the change in the taste and color of the sun dried onion and dried onion. Next slide will give you the pictures of those things. So these are the onion slices kept directly under the sun, and this was the color of these onion slices after 16 hours. The color is little bit degraded, and there was little bit fungus was also seen in these onions. Whereas these are the trays, loaded trays in the dryer, and this was the dried onion. So there is almost no change in the color, right? And these are the weights of the dried and wet onion in various trays, and the total moisture removed. These dried onion slices are tested for their nutritional values also. The test trial and nutritional trial done at authorized uh, uh, FSSAI, as per FSSAI norms, means all the food products have to be uh, passed through this particular test, and then only it can be called as food grade product. That the test is called as nutritional labeling. The sensory evaluation was also made, means the panelists of age ranging from 23 to 53 have tested the dried onion slices, and they rated the product as 7.8 against 9 scale. So it is the test, the sensory test was also passed. And the parameters, so moisture, earlier moisture was 86.6 and the final moisture was 73.93. Protein was also concentrated, fat was also concentrated, carbohydrates are also concentrated. So only moisture is removed and the nutrients are concentrated in the product. Similarly, chickus were also dried. Let me check the time. Chickus were also dried. So about 10 kg fresh ripened chickus were procured from the market. Not from the market. He was one of the clients. He was having his chiku farm in Vasai, and he was interested in drying the chickus because chiku is very perishable material. Once it is ripened, within 3 days, chiku will get perished. And if you dry it, its shelf life increases from 3 days to 1 year. Okay, so similarly here also 8.07 kg chiku slices were loaded in the dryer, and after 16 hours they have dried up to 5.57 kg. 65% moisture was removed from those chikus with the drying efficiency of 25%. And these are the diagrams. So these are the fresh chikus. These are the chikus dried at day 1, and these are the finally dried chikus. I myself have used these chikus for almost a year. There was no fungus, there was no change in taste, and nothing has happened. I ate these chikus for almost a year. These chikus are also passed for nutritional labeling, and The sensory evaluation test was also passed. The panel has given 8 points out of 9. The testing panelists were all female, and these are the concentrations. So protein is also concentrated, fat is concentrated, carbohydrates are concentrated, sugar, earlier they were unable to trace the sugar, but after drying 52 units of sugar were found in the dried chiku. Energy has also concentrated. So only moisture is removed and all other nutritional parameters are concentrated. This is the case study for onion drying, the economics. Okay, and if you see here, hardly 13.2 months is the payback period if we exclude the subsidy which government is going to give, and if we include the subsidy, less than 1 year is the payback time for this particular dryer. What are the highlights of this product? It's a simple and modular design, can be built and deployed in rural setting. It gives one screw heating. Ambient air is heated more than 100 degrees Celsius in the single collector. The collector has given a very high efficiency ranging from 70 to 74%. Average collector input was 4.6 kilowatt hour per day per meter square, and hot air delivered is about 3.4 kilowatt hour per day per meter square at 70 degrees Celsius. These are the average values. Peak value, I have mentioned that collector has given 119.6 degrees Celsius hot air in one of the trials. Pressure drop was very less, and because of that we were able to use DC fan, and which has consumed a very less power, hardly 20 watt. It is a grid independent collector and dryer. It is very lightweight, that 11 kg per meter square for 2.5 meter collector, and it has very affordable price. So cost per unit heat delivered is hardly 1453 rupees, and heat delivered per unit investment means if you invest 1 rupee, you will get 2.3 watt hour per day heat. If we if you would like to have the numbers in rupee, the cost of the collector is hardly 10,000 rupees per meter square. Sorry, 6,000 rupees per meter square. A very affordable price. What is the impact on energy users? Solar air heater without any auxiliaries, so 100% saving in energy. So no outside energy is used in the operation. So it will give very high net energy delivery. It requires very less energy to manufacture because all the components are energy intensive components. It delivers several years of service without significant maintenance. So the first dryer which I installed in one chiku farm in Vasai in 2016, it's still running without any maintenance. It can be deployed for tea drying, industrial air heating applications, or agro-produce drying, and can be offered for space heating, solid and liquid desiccant regeneration, desalination, effluent concentration, solvent vaporization recovery, and plastic drying. The space heating is very important application. In Leh, in couple of hotels, we have installed these dryers for room heating. Even in Germany, one of our clients is commercially selling this air heater for room heating in Germany. The DST has generously supported this particular project with the funds of about 40 lakhs, and I am thankful to DST for funding this project. And various industrial partners have also generously supported with the financial assistance during the tenure of the project. So that's all from my side, and thank you very much. My contact information is given in the slide. For further details, if you want any clarification, any additional information, please feel free to contact me. Thank you so much. I am open for the questions now. It's almost 2:40 now, so we have about 15-20 minutes for questions. I am well
Good
within the
afternoon,
time,
sir.
I guess.
Good afternoon, sir. Myself,
Yeah.
Professor Ratna. Sir, I have two questions from Dr. Bhusnur, sir.
Yes.
First question is, what are the different methods used to increase the efficiency of the solar collector?
Okay. What is the another question?
Another question is, at what optimum heat flux and temperature FPC will give maximum efficiency?
Pardon?
At what optimum heat flux and temperature FPC will give maximum efficiency?
Okay. Okay. I'll answer the first question first.
Yes.
The question was, what are the methods used for increase the efficiency of the solar
Of the
dryer?
solar collector, yes.
Okay, solar collector. We have used very simple technique, Dr. Busnur. We have tried to minimize the losses. The top loss was reduced by almost 50% by using multiple covers of plastic. Multiple glass covers will increase the weight and cost. So we have replaced the glass by polycarbonate sheets, and it was a multi-wall polycarbonate sheet. So it has helped us in reducing the uh, top loss. One thing, okay, one major component. Another thing is side loss. So we have given the air entry manifolds from the sides, so that the side wall temperatures are maintained near to atmosphere. So it has reduced the loss. And third is the fast conversion of absorber, the fast transport of absorbed heat to the heating material. Okay, so for that we have maintained laminar zone. We have decoupled the uh, solar heat transfer, air heat transfer coefficient and the pressure drop, because we wanted to have a very low pressure drop also. So maximum heat transfer coefficient in the laminar zone was achieved, and again inside corrugated tubes were used, so that the inside heat transfer area was used. So the simple methodology which we used was reduce the losses and increase the absorption, so that automatically efficiency will get enhanced. That was the methodology or technique we used in increasing the efficiency of the solar collector. Now another question was, at what heat flux and at what air temperature the flat plate solar collector gives maximum efficiency, right, madam?
Yes, sir.
Yeah. So commercially available collectors are giving different efficiencies at different temperatures. But if we consider the heat transfer aspect, the as the solar intensity increases or the hot air temperature increases, the efficiency reduces, because it absorbs more heat and the temperature increases. As the delta T increases, the heat loss will increase, and the efficiency will be reduced. So whatever the literature I came across, normal flat plate solar collectors practically uh, are giving comparatively good efficiency at around 700 to 750 watt per meter square of solar intensity. And the efficiency, the commercial average efficiency recorded is about 50 to 60%, 50 to 60% at hot air temperature of about 60-65 degrees Celsius. Yeah.
Okay, sir. Thank you, sir. Sir, there is one more question from Professor Parmeshwar Kaur. India has large areas surrounded by sea. Can't we use wave energy for power generation?
Yes, we can use the wave energy definitely for power generation, but there are some technological glitches. The technology is not yet that developed to be commercialized. They means, see, whenever we have to install some power projects, power plants, we need to think about the commercial viability of the project. So referring to ocean power technology, ocean wave conversion into power, the initial investments required are very high and huge at this moment, but people are working on that. Soon they may come up with very excellent technologies, and uh, then the conversion of ocean waves into power will become commercially viable. But of course, that is one of the options our government is also trying.
Thank you so much, sir. Now I conclude question answer session. Now I request Professor Mukund sir to give vote of thanks. Over to you, Mukund sir. Over to you, Mukund sir.
Yes, madam. It is my privilege to propose a vote of thanks on this occasion. I, Professor Mukund Valse, on behalf of MCT's Rajiv Gandhi Institute of Technology, Department of Mechanical Engineering, and on behalf of Organizing Committee of AICT AQIS sponsored online 1-week short-term training program phase 2 on recent trends in energy management and audit, and my own behalf extend a very hearty vote of thanks to Dr. Sandeep Doshi sir for accepting our invitation as a resource person and sparing his valuable time with us. He has given a good insights on the topic of conventional energy sources and its limitations, need for non-conventional energy sources, Indian energy scenario, renewable energy in India, wind energy, small hydropower, solar energy, SPV, solar grid power generation, and SWH. Also, he has focused on the HRD strategies, solar agro producer dryer. Thank you very much, sir, for your valuable guidance. Tomorrow on 24th November, morning at 10 a.m., we have the day 2, session 3 by Mr. Ravindra Datta, sir, on the topic of green audit for colleges and universities and energy conservation case study. I request all the participants to join the session. Thank you. Thank you very much, sir.
Yeah, thank you, Mukund sir. Thank you all the participants for patiently listening to me. Thank you everyone. Thank you, Kale sir, Bukade sir, NKD sir. Thank you very much.
Yes, thank you, sir. Thank you.
See you. Bye bye.
Bye, sir.